Good evening. This video here goes out to Hythloday and Logic Rolls the Dice. I wanted to put this out there. This is related to Asperger's, and I was never diagnosed as an Asperger's person. Didn't go to psychiatrist much, so that has to be part of it. But I was pretty introverted as a kid and found it hard to read people and was more into numbers and patterns and drawings and whatnot. But I kind of got over it. I still have some Asperger's-ness, especially when I'm alone, but when I'm around other people, I'm not bad at reading them and manipulating the situations into things I would want them to be. So, I'm going to tell you about how this came about for me, but only at the end. First, we're going to do a little bit of mathematics so that, once again, I don't want people on the YouTube thinking that I'm illogical or something. So I use plenty of math, which seems to have a nice intimidation factor. Tonight we've got something very special. It's called The Unpleasant Punisher. Behind this here is The Unpleasant Punisher. It's an article. This presentation tonight is almost exactly straight from an article by William Heller and K.K. Seberg called The Evolutionary Logic of Righteous Resentment. It was published in 2008. And this is a non-monetized video. I thought I'd point out that I'm going to fair use whatever I use. I'm just doing it for fun and educational purposes. My usual disclaimers here, like if I'm talking about rational, I mean self-interested. It's an economist thing. I'm going to try and say self-interested as much as possible, or rational self-interested, or try and put these things together to try and make more sense. Also, there's a concept in here called ESS, which is Evolutionary Survivable Strategy for our evolutionary logic. It's usually called Evolutionary Stable Strategy, but that term, when I was doing the research for this, turned out to be mean something different than I thought it was. So I have my own term, Evolutionary Survivable Strategy, that I'm using, and it means something slightly different than what they typically mean by evolutionary stable strategy. Okay. Ta-da. Okay, so this was based, there was a, if you want more information, there was a video on YouTube from Numberphile. It was called Rock, Paper, Lizards. And this video is a lot to do with that math. So if you want more information, that's Rock, Paper, Lizards is a good place to go. Basically, we're going to be doing this kind of rock, paper, scissors game strategy, but and they were showing how it's related to these lizards, right? There's 3 different types of this one species of lizard with the males. There's a monogamous lizard and a sneaky lizard and a dominant lizard, right? And so a monogamous lizard would have one mate, but a dominant lizard is bigger and likes a big harem and will come steal the mate from the monogamous lizard because it's bigger. And it likes a big harem of girls, of female lizards. So there's this other lizard called the sneaky lizard that's small. It looks like a female, and it's able to sneak into his harem and mate with the females. The dominant lizard won't notice. But a monogamous lizard would notice, and the monogamous lizards beat the sneaky lizards a little bit bigger than the sneaky lizard. And the population goes round and round and round, and this is an evolutionary strategy, right? It's like rock, paper, scissors, where there's no one specific strategy to play. They're all about the same. The difference between rock, paper, scissors, I have them slightly different colors, is that they're exactly the same, right? Where the lizards have some differences to them, right? And the way we're going to be talking about these differences tonight is through a model where there's cooperative people, there's cheaters, and there's the Punisher. And we'll talk about that quite a bit. But my hypothesis here is that cooperation relates to the Asperger's people. They're very logical. They believe in truth-telling and that kind of stuff. Where the neurotypicals, what you typically see around, are these people that are very interested and they really need the acceptance of other people, and they're willing to cheat to get it. They will lie about things they've done and make themselves seem better than they were, and do whatever it takes to try and get approval from other people, including like when they're in a group, they might exclude a black sheep person to try and gain favor with the group, right? And the other personality type that the psychiatrists talk about is the sociopath, and this person's more interested in the relationships between the people. He doesn't care so much if he's liked, just more looking for respect and to manipulate. He's a master manipulator, and I'm relating him to this Punisher type, but we'll get more into that at the end of the thing. Now, this is all economics, and this is going to be, we're going to be doing dynamic non-equilibrium models. Recently I've been talking about the equilibrium models, right? Supply equals demand kind of thing. And these are, I don't want to diss on equilibrium models too much. Like, they're very useful. We have a whole established price theory built on them that has been empirically tested and whatnot. So these are useful for a lot of things. But in equilibrium, there's no change. In an equilibrium system, when a system's in equilibrium, it won't change unless there's some outside force that comes in and affects the system. And we need more drama than that. Economics is best as the dismal science, and the more dismal you can get, the better. But economics is best as a form of dystopian science fiction, such that I'm just going to take utopias and crush them. And that's the best way to do this, the dismal science. So we're going to need more drama. And I'm saying these circles are going to be a good way to do it, right? Like, it's really hard to explain the Industrial Revolution with an equilibrium model, right? What's going on is in the Industrial Revolution, we get more coal, which leads to more urbanization, which leads to more technology, which leads to more coal, which leads to more urbanization. We need a circular argument in order to explain a positive feedback loop, right? Ever since the Industrial Revolution, everything's been taking off on an exponential curve. And so there can't be one force for that. If there is, like before the Industrial Revolution, they'd come up with some new technology and population would increase and it would cap off at that new level of technology, and then wait a couple more hundred years until a new piece of technology came around, and then population would exponentially grow until it hit the cap for that next piece of technology. Once the Industrial Revolution started happening, this all became a positive feedback loop. And as economists, we're just figuring this out now. It seems kind of an obvious thing, but the circle really wasn't complete until this guy Moke here started talking about how, well, during the Industrial Revolution, coffee shops and things like academic journals started taking off also exponentially. So if you want to say it's any of these things, you've got as much empirical evidence saying that coffee shops is also taking off exponentially. And while economists don't want to think about people sitting around talking BS about morality in the coffee shops or on YouTube as productive, it actually is the thing that is the market of ideas and leads to technology. And that completes the circle there. And so we're very interested in having this kind of thing, more coffee shops in underdeveloped nations. And then also I want to talk about Victory Clark Grove real quick, right? That with this circular idea of the rock, paper, scissors, that we might beat that Victory Park Grove problem that I'm always talking about, right? Where we can't, the Victory Park Grove is an impossibility theorem. It says we can't design a system that doesn't let people trade and they must participate and they have to be truth-telling all at the same time. You can't build a system that does that. Whereas we might be able to build something that they have to trade off and circle around through the different strategies. And I think this could be a new foundation for economics, this kind of circular things. We just need to build a price theory on it. And I think this guy, Professor Steve Keen, he's a economist out of Australia that's on YouTube a lot. And he's got this program called Minsky that does macroeconomics with these kind of circles, and is able to predict things pretty well with it. So that's the introduction. We're going to do a little bit of review. There's this is all based on game theory, these circles. So really briefly, this is Prisoner's Dilemma. It's a game people are very familiar with. In this game, we look for a Nash equilibrium, which turns out to be this 1-1. If they're at this spot, the green guy could do better by going down to this one. If they're at this spot, the yellow guy could go, the purple guy could be better going to this way, right? So this is not a Nash equilibrium, but this one is, because the green guy would get 0 if he switches, and the purple guy would get 0 if he switches here. So then they're going to get stuck at 1-1, even though it'd be better for both of them if they were at 3-3. This is also, we're going to introduce the evolutionary, let me put out the word, evolutionary survivable strategy as well. That in a population of cooperators and defectors, the cooperators would go extinct. We'll get more into that as it goes on. This is Matching Pennies. This is my example of a game without a Nash equilibrium, but this does have a evolutionary survivable strategy. Right, if they're here, the green guy, no, the purple guy would be better off by going here. If they're here, the green guy would be better off going here. If they're here, the purple guy would be better off going here. If they're here, the green guy would be better off going here. And so it's just going to go around and around and around and create this kind of circle we're looking for. This is basically the very simple version of rock, paper, scissors. This is no Nash equilibrium, but these are both evolutionary survival strategies because it'll keep going around. Not one will get dominated by a different strategy. So the game we're going to play tonight is Cooperation. And cooperation is kind of hard to explain through the economic lens of self-interested players. The world is full of these self-interested players, and that could make things hard to, why do people cooperate, right? Like in this Prisoner's Dilemma, when we do play it in the real world, people don't always go here. They often do cooperate with someone they have never heard of before, they've never even met them, and they will cooperate them even though that person could mess them up by going to a different spot. Sometimes that happens too. But mathematically we would say that people will never cooperate, but in the real world we do see people cooperate. But it's kind of a mystery because cooperation is going to have low reciprocity in large communities. If I cooperate with people at the grocery store and don't cut them in line, it's not likely that I'm going to see them again. So there won't be a return on cooperative behavior. There's also collective action problems, such as communism, the principal agent problem, like having workers do what you want them to, other collective action problems like the Arrow impossibility theorem that I've gone over. So it's really hard to model cooperation. Here's the cooperation game. and it's going to be a little complicated. We're going to get into some details here. Okay. We're going to call, it's going to work a little bit different than Prisoner's Dilemma, but it's kind of the same idea. But Prisoner's Dilemma had two different scorings on each of the squares, and this one has one payoff per square. So if F, a fair player, plays against another fair player, he will get alpha, which is the benefit for fair play. If a fair player plays against a cheater, the fair player will get alpha minus beta, where alpha is the benefit of fair play and benefit is the cost of being cheated. Now we don't know, sometimes the cost of being cheated is bigger than alpha, and sometimes it is smaller than alpha, right? Sometimes someone cheats us and we get hurt just a little bit, sometimes we get hurt a lot. We do know that beta is greater than 0. We're going to call the symbol that we call the cheater's payoff, if he cheats against a fair player, we call that 1. And that's the benefit of cheating. And cheating is bigger than alpha. If the benefit of cheating wasn't bigger than the benefit of fair play, then there'd be no incentive to cheat, and we wouldn't have a model to talk about. So 1 is bigger than alpha. Boom. So we can try and figure out how this payoff matrix is going to work. We'll talk about this square. I guess I haven't talked about this. When a cheater meets a cheater, then one wins half the time. So sometimes they get 1 point, and the other half of the time they get 1 minus the cost of being cheated. And then since each of those is half the time, we divide it by 2. So now we want to figure out which of these numbers is bigger than the other numbers. So if the guy that you're playing against is a fair player, then you can either fair play or cheat. And we've already said that 1 is bigger than alpha. So in that case, you would be a cheater. If the other person is a cheater, well, okay, this is a bit more complicated on these. Is alpha minus beta more than 1 plus 1 minus beta over 2? So we're going to analyze this. Is 1 plus 1 minus beta over 2 bigger than alpha minus beta, right? These guys. And when we solve that for beta, we get beta compared to 2 times alpha minus 1. And since alpha is less than 1, then this part's negative, right? And since beta is bigger than 0, then this part's positive. So beta is bigger than 2 times 1 minus alpha, which makes this bigger than this. Basically, beta is bad, and this guy only gets half of beta, is one way to think about that. So cheat is better against fair players, and cheat is better against cheaters. Therefore, cheating is going to be the Nash equilibrium, is going to be the evolutionary survival strategy, and the fair players will go extinct. That'll make more sense when we get to explaining how the evolutionary games works, but we're kind of starting with your basic kind of idea of game theory and kind of Nash equilibrium, and moving into evolutionary survival strategies. But in this one, right, the C's completely dominate the F's, and the fair players will go extinct. So what keeps people from cheating is the Punisher. But the pure Punisher has some problems because he violates self-interested rationality, right? There are some costs to punishing. It takes some action, some time, some effort into punishing somebody, right? And so there's cost, but very little direct benefit, right? The low reciprocity in large societies, it's you're not going to be thanked by the people that were being cheated. They punish even when they're not. Like if someone else is being cheated, they'll punish. So it doesn't directly benefit them. And so they're just kind of doing it for the good of society, right? So they're taking on a personal cost to themselves without any direct benefit. So this is a type of altruistic sadism and violating self-interested rationality. So instead, we have the unpleasant punisher, and this guy is not your altruistic guy. This guy is your straight-up jerky-faced jerk. And through that, he gains self-interested rationality by using a use of mixed strategies, right? He punishes the cheaters, but also cheats himself. And so this requires some ability to be able to read the other individuals and kind of guess their strategy. And so Asperger's people do say that, they have a hard time doing this, but it's not impossible to learn. People aren't that complicated. You can see when someone is sad. You can get a good idea when someone is lying. Some people are better at deception than others, but in the most part, it's not too bad a thing. And I think it's some work that you can certainly understand romantic comedies for the tripe they are. Basically, we're going to assume that he's got 100% success rate at guessing, so that we can do our payoff matrix a lot easier. But you can add risk to the model and put in probabilities of being caught and not being caught. Of guessing the opposing player's strategy. But again, I say it's not too bad. So we've got this type of person, and so now we can include them in a game and make the 3x3 cooperation game, right? We've got fair players, we've got the cheaters, and we've got the unpleasant punisher. You is the unpleasant punisher. Oh yeah, so this is going to get pretty complicated pretty quickly. Let me just run through the variables. Alpha is still the benefit of fair play, 1 is still the benefit from cheating, and beta is still the cost of being cheated. But we need to add that cost of punishing we're talking about, that it requires some energy to punish. We're not going to add any benefit for punishing because we haven't declared that. And we do add y. Y is the cost of being punished, like the punishment itself. And so for our hierarchy, we're going to say that y has to be bigger than 1 minus alpha. The difference between cheating and fair play, that you have to create a disincentive out of it. So at the very least, y has to be bigger than 1 minus alpha. And again, it's going to come down to our hierarchy of variables. What's bigger than what, so we can figure out all of this. To make it simple, we're going to say 1, the benefit of cheating, is bigger than the punishment, y, which is bigger than alpha, the benefit of fair play, which is bigger than beta, the cost of being cheated, which is bigger than, I'm going to call it theta, although it's not, but I'm going to call it theta, the cost of punishing. Now this is a sufficient hierarchy, like this will meet all the requirements, but it's not a necessary hierarchy. Like we could switch y and 1 and still be okay, or we could switch the hierarchy between y and alpha and still be okay. And we'll talk about what that does next. But first, we'll go through the payoff matrix, right? So this square part, right? I'll just zoom in. Boom. This square part is the same payoff matrix we had before. So we know that 1 is bigger than alpha, and we know that 2 minus beta over 2 is bigger than alpha minus beta. And then we're going to add in the unpleasant punisher. Okay. There's going to be some indifference here between the cheater and the unpleasant punisher, because they're both going to cheat the fair player and get 1. But we know that alpha is still less than 1. And so fair player is not going to do good here. The cheater is going to do really well, and the unpleasant punisher will do equally well. But we'll give this one to the cheater. On this one, when the population is cheaters, fair play will get alpha minus beta, and we know that 2 minus beta over 2 is bigger than alpha minus beta. But this one is the basically half the time. Okay, so this is the unpleasant punisher versus the cheater. And sometimes the unpleasant punisher will cheat the cheater, and sometimes they will punish the cheater. And so it's going to look very similar to this one, right? Where we're going to divide by 2. But they have to pay that cost of being punished, or the cost of punishing half the time, because they're the unpleasant punisher. And so then, I mean, this is basically the same thing. We just got to look at beta and theta and see which these, and in this one we're saying that beta is bigger than theta, right? So the unpleasant punisher will dominate on this one. Now this one's more complicated, right? They both got this. So what's happening here is there is the cost of being punished, and sometimes a punisher will punish another punisher, and sometimes they'll cheat them. When they do punish the other punisher, they have to pay the cost of punishing, and when they get punished themselves, they have to pay the cost of being punished. And it's similar with the cheater. But again, it's the difference between this alpha and beta thing here. But the thing is they both have to pay Y, and Y is pretty big. Y is the punishment, and the fair player doesn't have to get punished, and the fair player is going to win this one. So it's going to go around and round and round between the 3 evolutionary strategies, and they will all be evolutionary survivable strategies, and the population will go round and round and round like the lizards do. So to talk about that, we need to do a little bit of explain what's going on with the math. We need to create what's called a simplex, which is basically just taking a 3x3 model and mapping it onto a 2x2 model, so it's nice and flat. We can draw it on a piece of paper. So here's an axis with the amount of the population that are unpleasant punishers. Here's the an axis with the percent of population that are cheaters, and here's an axis with the percent of population that are fair players. So here at this point, it's 100% fair players, and it's got zero unpleasant punishers, and it's got 0 cheaters, right? This is 100%. This one's 100% unpleasant punishers, and this one's 100% cheaters. And we can draw a equilateral triangle between these 3 points, and everywhere on that plane is where the combinations of the population equals 1. So everywhere on this triangle, the percent, the proportion of the population of the percent of the population that is fair players plus the percent of the population that is cheaters plus the percent of the population that is unpleasant punishers will equal 1 everywhere on this plane. And so then we can draw that plane nice and flat here, right? So this point here we can say is 20% fair players, 20% unpleasant punishers, and 60% cheaters. So that's where the space where we're going to play the game. And so to play these kind of evolutionary games, we're going to need a computer model, and we're not really going to do that. But here's the idea: is we have some starting mix of the population, such as 20%, 60%. And then the strategies will grow or die off based on the amount of points they get. And then we keep iterating the model with the new population mix that were from when they grow and die off. And let's say, and this will either, we can iterate the model. It'll either end up at one of these extreme ends, like maybe it'll end up, not likely, maybe it'll end up with everybody being cheaters. Maybe it'll end up with everybody being unpleasant punishers. Or it might create a what we call the fixed propeller point. Is that what I said? No, or then we're going to find a propeller point if it doesn't go to one of these spots. And this is a place inside the model where it's going to keep spinning around and around. Here in the middle, right, we've got rock, paper, scissors, because there's no real difference between, like if this was a rock, paper, scissors evolutionary game, it'd be right in the middle, because there's no difference between rock, paper, scissors, and they would spin around, maybe even hit an exact point in the middle where everything's 33% and just be there. Where we can get to other points in this graph and have these other propeller points when, depending on how we did our hierarchy of variables, like what is bigger than what and by how much, is going to create other spots in the map where where it's going around where if it's a population of cheaters, then it'll become more and more unpleasant punishers, and it'll come around to be more and more fair players, then become around here more and more cheaters, and more unpleasant punishers, and more fair players, and then more cheaters, then more, and they're going to do this evolutionary stable strategy thing. And there's some right combination of variables where we can get like populations of 80% fair players. But the whole point of this is to do that, you need these unpleasant punishers. You need these jerky people in order to have fair play societies. And so where are we right now? Well, if we look, if what I'm saying in the beginning part was true, that the mapping from cooperative goes to Asperger's, and the cheaters map to the neurotypicals, and the punishers map to the sociopaths. Then right now we're mostly in neurotypicals, and they're so prevalent that typical is in the name of the personality type. So right now is a really good time to be the unpleasant punisher, to be the sociopath. And so that's the conclusion, is that you can have more sociopathy in your life and use mixed strategies. Don't be defined by these words like Asperger's. That you can work to change who you are. There is no self. There is only a simulacra of self that you create. And so obstacles can be overcome, such as reading people. And to do this, the way I got through it, in my opinion, I haven't really been diagnosed or anything, was to employ fantastical archetypes, these fantasy heroes. And there's plenty of anti-heroes to choose from, right? So on the days when I've had enough crap and there's plenty of shit in the world to be pissed off about, I might employ a personality type like Robert De Niro from Taxi or Cobra Commander from G.I. Joe and take the world on by storm. Now, I'm not saying going on a shooting spree, that's too much. If you're a complete jerk, like some of these guys, people aren't going to like you and it's not going to work out well. But you can employ parts of their personality into your own to create a more dynamic strategy of personalities inside yourself. Again, shooting spree, that's too much. I'm saying be more sociopathic, not psychopathic, right? That's a big point there I need to make. Don't go out and be a dick, but you can be assertive. What I'm saying, just to drive it home, this right here, logic rolls the dice, this is part of you if you choose it, if you embrace it. Thank you for watching. It's been a pleasure speaking with you all.